All right, so this is the review that I would have done on Labor Day. We've seen when talking about linear independence, linear combinations, and span, we've seen the need to know how to solve a linear system of equations. So in this review, we're going to focus on learning a certain algorithm for how to solve a linear system of equations. And we're just going to do a sort of a deeper study of them to better understand how they work. To start with, let's look at a simple example. You guys have learned a couple of different ways of how to solve this system. One method that you guys have learned is elimination. So the way that works is you want to try to combine your equations in such a way that you manage to eliminate a variable. In this example, what we can do is multiply the first equation by 2, and then subtract the equations from each other. If we do that, 2x minus 2x, so the x's are eliminated, that's our goal, minus 6y, minus a negative, so plus 5y, leaves us with minus y, and then we get 4 minus 1 is 3. From there, you can solve for y, and you would find that y is negative 3. And then to get x, we could look at the first equation again. We can substitute our answer for y into that first equation. And then from there, you are able to solve for x. All right, now taking a closer look at everything that we just did, what's actually important in our original system of equations? The coefficients are important. The right-hand side of our equation was also important. The variables x and y, they're actually somewhat not important. They may be somewhat superfluous, you could say. So one way you can kind of understand that is just by the fact that rather than using x and y for our variables, we could have used any other two letters like a and b, or f and g or whatever. So in some sense, the variables are not too important. They're not really needed. Or let's say you don't really need to write them. At least when you're doing the elimination. So what that suggests is that we can rewrite our system in a sort of more simplified form. Just by writing the coefficients of x and y, and then writing the right-hand side and dropping the variables. Okay. So this is what we would call the augmented matrix. For the linear system of equations that we have up top. Now, by augmented means that you're including the right-hand side of the system of equations. If we just look at the coefficients and just put those into a matrix, this we refer to as the coefficient matrix. Okay. Now, when we go back and think about what we did in the elimination, so we multiplied equation 1 by 2, and then we subtracted from the second row. So then that operation can now be viewed as an operation on the rows of this augmented matrix. So we could imagine taking the first row, multiplying it by 2, and then subtracting it from row 2. This is a little bit different from what we did, but it's the same idea. Okay, so if we multiply the first row by 2, and then subtract it from row 2, we get 2 minus 2, which is 0. We get negative 5 minus 3 times negative 2. So negative 5 plus 6 is 1. Then here you'd get 1 minus 2 times 2. So that would be, whoops, negative 3. And then this operation was only modifying the second row, because I was subtracting 2 of row 1 from row 2. So I just copied the first row down. And then if you take this augmented matrix and you write out the equations that corresponds to it. So the first row gives us the equation x minus 3y equals 2. The second row gives us the equation y equals negative 3. And so you see it gets us the same result as what we had up here. And then once you're at this step, you have y, and you can go back and substitute to get x, as we did earlier. Okay? All right, so we're going to do some examples of solving linear systems of equations by writing out the corresponding augmented matrix and then performing these row operations to eliminate some variables, all right? So let's illustrate with a 3 by 3 example. Well, actually, before that, I should go over the process. Okay, so solving, linear systems of equations. And we're going to do that by performing some row operations on the augmented matrix. And first, we should understand the types of row operations that we can perform. So most people break it down into 3 types of row operations. So earlier you saw that we did the operation row 2 minus 2 of row 1. So we can add or subtract a multiple of a row to another row. This is the type of operation that you're going to do the most of. This is the operation that eliminates variables in your system of equations, so it's the most important one, I would say. But some other types of row operations which are useful. We can swap rows. So that's just the idea that, when you look at, say, these two equations, if I switch the order and put this one up top and then put this one on the bottom, that doesn't actually change the system of equations. So therefore you can swap rows. That's okay because it doesn't change your system. Last, you can also multiply a row by a non-zero number. So that would correspond to, say, multiplying this first row here by a number. That would just correspond to multiplying both sides of this equation by that number. And of course, if you multiply both sides of an equation by a non-zero number, it doesn't actually change the equation. Or rather, you get an equivalent equation. Okay, so therefore, these 3 types of row operations, these are things that you can do when you are trying to solve a system. They will produce an equivalent system so that you're not changing your problem by doing these row operations. Okay. All right, so we're going to do some examples of performing row operations to solve some systems of equations. I would like to do a 3x3 example right now. So let's do x plus y minus 2z equals 3, negative 2x minus y plus 3z equals negative 5, 3x minus 2y minus 4z equals 1. So to solve this system of equations, we're going to convert it into an augmented matrix. So I'm going to write out the coefficients of x, y, and z. So this would be the coefficient matrix. I'm going to augment it by adding the right-hand side. Okay, so that's our augmented matrix. And what I'm going to do is I'm going to perform some row operations to eliminate the negative 2 and the 3. That would correspond to eliminating x's in the system of equations. So if I want to get rid of the negative 2, I could take row 2 and add 2 of row 1. So when I multiply row 1 by 2, I get a 2 here. And then adding it to row 2, I would eliminate the negative 2, and that would produce a 0 there. So let's do this operation right now. Okay, so we just talked about how this will become 0. Going to have negative 1 plus 2 is 1. 3 minus 4 is going to be negative 1. Then negative 5 plus 6 is 1. Now I also want to eliminate this 3 here. So I'm eliminating this x is what I'm trying to do. So I can eliminate the 3 by doing row 3 minus 3 of row 1. So we would get 3 minus 3, negative 2 minus 3, negative 4 is going to be plus 6, so 2. And then 1 minus 9 is negative 8. Okay. Now, after that, what I'm going to do next is I'm going to eliminate this negative 5. And so to eliminate the negative 5, I'm going to do row 3 plus 5 of row 2. If I did that, so first we get 0 plus 0. So this remains a 0. Negative 5 plus 5, 0. 2 minus 5, negative 3. Negative 8 plus 5, negative 3. Okay. And then we'll copy the remaining rows down. And so now I've done some row operations and I've gotten to the point where my system is in a sort of upper triangular form. So upper triangular form means that you have zeros beneath the diagonal. And so all of the non-zero entries are in the upper triangle. That's why we call it upper triangular form. Okay. So usually when you're solving a system, your goal is to get it into this upper triangular form. The reason why we do that is because now if I write out the system of equations that corresponds to this augmented matrix, well, the first row gives me the equation x plus y minus 2z equals 3, y minus z equals 1. That's the second row. Third row is just negative 3z equals negative 3. So notice that the last equation, you are now able to solve for z. Then you can plug it in to the second equation, and you'd be able to solve for y. So plug in 1 for z, and then solve for y, we'd get y equals 2. Then finally, we can plug in y and z into the first equation. So we'd get x plus 2 minus 2 equals 3. And so x would be equal to 3. Okay. So this process that we just did of solving the system of equations, there's two parts to it. First is doing the elimination. I'm not sure if I'm spelling that right, actually. Well, whatever. So elimination. So that corresponds to doing all the row operations to get it into the upper triangular form. Then there's a second step, which is this part over here, which we refer to as back-substitution. All right, so it's back substitution because we start with the last equation and solve for z, and then we're substituting it back into the previous equation to get y, and then substituting back into the first equation to get x. All right, so back substitution. All right. Now, taking a closer look at the process of elimination and seeing how that worked. So first, you focus on getting zeros in your first column. And so I used this 1 in the first row to eliminate the -2 and the 3 beneath it. So this 1 here that I just circled, we refer to as the pivot. So your goal in elimination is to use your pivot to eliminate everything beneath it. Okay. So then over here, similarly, so this was the first pivot. Then what we did was we used this guy to eliminate the -5 beneath it. So then this guy would have been our second pivot. And so in general, the pivots are the entries that you have on the diagonal that you end up using to eliminate everything beneath it. Now, the numbers that we use or the numbers that we multiply the pivot by in order to eliminate, those are called the multipliers. Although the way it works is a little bit weird. So this is just because of the way that your textbook talks about this process. Okay, so when you look at the row operations that you did, here I did row 2 plus 2 of row 1. Okay, so I multiplied row 1 by 2 and then added it to row 2. So the multiplier that I ended up using in this first row operation is not plus 2, but minus 2. I'll explain why in a bit. But similarly, in the second row operation, where we did row 3 minus 3 row 1, the multiplier that we used for this row operation is not minus 3, but plus 3. And finally, the multiplier that we had over here in this row operation is minus 5, not plus 5, as you see here. So it looks kind of weird, but I'm taking this number that we multiply the row by, and we just change the sign to get the multiplier. The reason why is because in your textbook, all row operations are done using subtraction. So the first row operation, row 2 plus 2 row 1. If you write it as row 2 minus -2 row 1, the textbook says that this -2 is the multiplier. And then likewise in the second row operation, when we did row 3 minus 3 row 1, so the textbook takes this 3 to be the multiplier, and row 3 plus 5 row 2 plus 5 is the same as minus a -5. So that's why -5 ends up being the multiplier. But personally, the way that I think about it is just whatever number you have here, just change the sign and you get the multiplier, okay? So a little bit weird, but Again, it's just because of the way your textbook does it. Your textbook does all row operations as subtractions. Okay, so just wanted to get you guys to understand the procedure. So I'll summarize one more time, and then we'll do more examples, of course. You take your pivot, which is going to be the first entry in the diagonal. Use your pivot to eliminate everything beneath it. Then move to your next pivot. Eliminate everything beneath it. Keep going until you get the upper triangular form, meaning you have zeros beneath the diagonal. Then route out your corresponding system of equations and back substitute to get the solution. And then when asked for multipliers, remember that the multipliers are, assuming you write your row operations the way that I do, the multipliers, if you're asked for them, are the opposite of the numbers that you used in your row operations. Okay. Now, before I do a couple of other examples, I want to talk about something called the row picture and the column picture. Okay, so to illustrate what these are, we're going to look at a simple system of equations. All right, so you can actually work it out and get the solution. If you do, you would find that x was -1 and y was equal to 2. All right, so the row picture this is probably something that you guys are already familiar with. The idea of the row picture is that each row or each equation represents the equation of a line. So what we're going to do in the row picture is we're going to graph the two lines represented by our equations. So the first equation is the same as y equals 3x plus 5. So it's a y-intercept of 5. And then the slope is 3, so if I go up 3 and over 1, then connect these two dots. All right, so that's the line described by our first equation. Our second equation, if we rearrange it and solve for y, you should get y equals -1/2 x plus 3/2. All right, so then graphing this, the y-intercept was 3/2, and the slope is -1/2, so let's see here, let's go up 1 and then over 2, and then connect these two dots. All right, so then that would be our second line, and where the two lines intersect each other, that should be where the solution lies. So where x is -1 and then y is equal to 2. Okay. And so the idea is for a point to satisfy both equations, that would mean that it would have to lie on both lines. Hence, where the lines intersect, that will be where the solution of the system of equations is. And what's important about the real picture is that it gives us some insight into what a solution to a system of equations might look like. Okay, so we've seen the possibility of having, two lines intersect at a point. And since they only intersect at one point, that means there's only one solution. But another possibility is maybe your two lines are parallel to each other so that they never intersect. If that's the case, then there would be no solution. To the system of equations. So an example of this might be something like x plus y equals 1 and x plus y equals 2. So these are the same lines, but they're just shifted up by 1 unit. So they would be parallel to each other. You can sort of already see sort of intuitively, it's not possible to have x plus y equal 1 and at the same time equal 2. So that this would be an example where there would be no solution. And then there's a third possibility, which is that if your two lines happen to be equal to each other, so they would just sort of sit on top of each other. In the event that your lines overlap, that means that they're intersecting at infinitely many points, meaning there would be infinitely many solutions. An example where this would happen would just be something like x plus y equals 1, and maybe like 2x plus 2y equals 2. The equations look different, but you see that they are actually equivalent to each other. The second equation is just the first one times 2. So they're the same line, so they intersect at infinitely many points, and you get infinitely many solutions. So every point on this line would be one such solution. Now this is just looking at 2x2 systems, 2 equations, 2 unknowns. But it turns out that this persists no matter how many equations and how many unknowns you have. It will always be the case that there will either be a unique solution or no solution or infinitely many solutions. You'll never just have, for instance, just 2 solutions. As soon as you have more than one solution, it must be that you have infinitely many. All right? So that's some insight that we get from looking at row pictures. We see that there's 3 possibilities regarding the number of solutions that you have. All right. So next, let's also take a look at the column picture. So to get the column picture, I'm going to take the system of equations and I'm going to rewrite it as x times 3, 1 plus y times negative 1, 2 equals negative 5, 3. So all I did was take the coefficients of x, 3, 1, and then multiplying by x, so I've got 3x and 1x. Likewise, I just pull the y out from its coefficients. So I've still got minus y and plus 2y. And then the right-hand side, negative 5, 3. Okay. So we took our system of equations and rewrote it. So now when you look at this equation, you see that what we're trying to do is we're trying to express the vector negative 5, 3 as a linear combination of the vectors 3, 1 and negative 1, 2. So if you will, we're expressing the right-hand side as a linear combination of the columns in the system. And as noted earlier, the solution to this system was x is negative 1 and y is 2. Okay. And so the column picture is just a picture illustrating how this particular linear combination of the columns produces the right-hand side. So I'm going to first graph or draw the vector 3, 1, and then also the vector negative 1, 2. And then next I'm going to multiply 3, 1 by negative 1. So multiplying by negative 1 just reverses the direction. Still be the same length. That's about right. So that's negative 1 times 3, 1. And then we've got negative 1, 2, and I'm going to multiply by 2 and draw that out. So multiplying by 2 would double the length. So maybe about here. So that's 2 times negative 1, 2. And then these two vectors, they should add to produce negative 5, 3. And remember that to add vectors, when they are connected tail to tail, you can think of the sum as being the diagonal of the parallelogram that they form. So here's the diagonal of the parallelogram, their sum. And if your picture is pretty good, you should see that this vector is roughly at negative 5, 3. Okay. So then, 3 is roughly up here, and then maybe 2, 3, 4, 5. Yep, so you can kind of see it's about negative 5, 3 in the picture. All right. So that is the column picture. And between the column picture and the row picture, I would say the column picture is maybe more important to keep in mind. as you continue your studies in this class. One thing that the column picture sort of reveals is that this system of equations will have a solution if and only if the right-hand side is a linear combination of the columns and the left-hand side, I'll say. Right, so because if you have a solution, then this would reveal that the right-hand side was a linear combination of these columns. And if there were no solution, that would mean that the right-hand side was not a linear combination of these columns. Okay? So that's some insight that you get when you look at the column picture. And as I was saying, I would place a little bit more importance on the column picture than the row picture. All right. Now, when we talked about the row picture, we saw that it's possible to have no solution, and it's possible to have infinitely many solutions. So I'd like to do an example of that. And so I'm going to do another example before that, but these next examples are going to be talking about something called temporary as well as permanent breakdown. I personally don't like this terminology, but it's something in your textbook, so I kind of have to talk about it. All right, so let's say that I'm going to illustrate what a temporary breakdown is in elimination. And then after that, we'll look at what a permanent breakdown is as well. Okay. Let's consider the following system of equations. If we try to perform elimination on this system, so first write out the augmented matrix. Okay. I'm going to take this first entry on the diagonal as my first pivot. I'm going to eliminate everything beneath it. So let's do row 2 minus 2 row 1. And then row 3 minus 3 row 1. That will get rid of the 2 and the 3. Okay. Oh, whoops. All right. Looking at what happens in the second and third rows. So row 2 minus 2 row 1. That will be 4 minus 4, 0. 1 minus 0, 1. 7 minus 6, 1. And then row 3 minus 3 row 1. So 4 minus 6 is negative 2. 2 minus 0 is 2. And 9 minus 9 is 0. Now remember, the goal of elimination is to try to get to the upper triangular form. So what we'd want to do then is we'd want to use our pivot here to eliminate everything beneath it. However, you can't eliminate anything with a zero pivot. So when you get a 0 in a pivot position, your textbook refers to this as a breakdown in the elimination process. And then they distinguish between two types of breakdowns. So temporary breakdown. This is when you are able to fix the problem by swapping rows. Okay. So for instance, in this example, I could just swap row 2 and row 3. And if I did that, that would solve all of our problems. So we would get a non-zero number up here, which we could use as a pivot. But then also we actually don't really need to do any more elimination, because once we swap rows, it's already in the upper triangular form. So we would stop. Okay, so that's an example of where a temporary breakdown occurs. You get a 0 in a pivot position, but all you have to do is swap rows, and that fixes your problem. Now that it's an upper triangular form, that means we can go ahead and write out the corresponding system of equations. So the first row gives us x plus 2y equals 3. Second row says negative 2y plus 2z is 0. And third row says z equals 1. So now you would just back substitute in order to get the solution. Okay, so here, if you move the 2y over, cancel the 2's, you get z equals y. So in other words, y would be equal to 1 as well. And then if y is equal to 1, move the 2 over, you get x is equal to 1. And so that gives you the solution. Okay. Now, sometimes you're not able to fix the breakdown by swapping rows. So in that case, that means that you have a permanent breakdown instead. So I'll try to illustrate that with an example. And let's see here. So I'm going to write out the augmented matrix for a system of equations. And let's try to do elimination with this new system. All right, so here's my first pivot. I'm going to use it to eliminate everything beneath it. So I'm going to do row 2 plus 2 row 1, and we'll do row 3 minus 4 of row 1. Okay. So we'll have row 2 plus 2 row 1, so negative 2 plus 2, 1 plus 0, 3 plus 7, 3 plus 4, which is 7, and 2 plus 6, which is 8. And then row 3 minus 4 of row 1, so 4 minus 4, 0. Negative 1 minus 0, 1 minus 8, and negative 2 minus 12, so negative 14. If we try to do another elimination, so using this as our next pivot, and we try to eliminate everything beneath it, we could do row 3 plus row 2. When we do that, notice that adding row 2 to row 3 will give you a row of zeros here. And then we're also going to get negative 6. Now, when you get the row of zeros like this, this is what the author of your textbook refers to when they say that there is a permanent breakdown. Now, if we look at the very last row and we write out the corresponding system of equations, or the corresponding equation rather, that last row says 0x plus 0y plus 0z equals negative 6. And clearly there is no solution to that. So therefore there's no solution to this system of equations. All right. So we talked about how it's possible to see that there will be no solutions in a system of equations. This is one example of that. Whenever there's no solution, you will know that's the case because you're going to end up with 0 equal to something non-zero. Once you get to the end of your elimination process. Okay. So it's really easy to know if you have no solution. Just do the elimination and you should get 0 equal to something non-zero. And that's no solution. Okay. Now, just because you get a row of zeros doesn't mean that there was no solution. Okay. So let's say that instead of having a negative 2 here, let's pretend that negative 2 was a 4 instead, all right? Okay. So if that negative 2 was a 4, let's see what would have happened. When we did row 3 minus 4 of row 1, we would have had 4 minus 12, and that would have given us a negative 8 here instead. And then when we did row 3 plus row 2, the 8 and the negative 8 would have canceled as well, and we would have gotten 0 at the end. So then all of a sudden your last row would say 0x plus 0y plus 0z equals 0. And there's actually nothing wrong with that, right? So I'm going to continue in green and let's see what happens. So writing out the corresponding system of equations, we have x plus 2z equals 3. And then we have y plus 7z equals 8. And since the third row is just all zeros, I'm just not going to write it down. All right, what's happening is we have two equations. So what I can do is I can solve for two of the variables. So if I solve for y in the second equation, we get y equals 8 minus 7z. If there were y's in the first equation, I would substitute this back into the first equation, and then I would solve for x. In this case, we would just get x is 3 minus 2z. All right. So we have a solution of sorts for x and y, but we don't have anything for z. So z is what we refer to as a free variable. So it's free in the sense that there's no restriction on z. So z could be any real number. Right? And so to reflect the fact that z can be any real number, people often assign a parameter to each free variable. Parameter just being like another variable. So I'm going to set z equal to t, and then I can rewrite x and y in terms of the parameter t. Whoops. And then the parameter t can be any real number. And so we have infinitely many solutions, one for each possible value of the parameter t. All right. So when you have infinitely many solutions, this is how you can express your answer in terms of parameters for each free variable. One thing I'll note is, going back to the problem, so notice that we only had the pivots in the first two columns. The third column is missing a pivot. If you can hear that, that's just my cell phone going off. So in general, whenever you have a column missing a pivot, that indicates the presence of a free variable. Specifically, since the third column was missing a pivot, that's why the third variable z ended up being a free variable. All right. So that's just something good to keep in mind. When there's a column without a pivot, that tells you that you have a free variable. And then the presence of a free variable means that you're going to have infinitely many solutions at the end. Okay. All right, so then I'm now going to talk a little bit about matrix vector multiplication. So this is something that I had intended to talk about last week actually, but I had taken too long with everything else in my review, so I wasn't able to get to it. But I suppose you guys are already decently familiar with matrix vector multiplication. So I won't take too long. Okay. When we have a system of equations, and I'm just going to write down a generic 2x2 example. We've learned how to express this system in many different ways. So one way that we can represent this system is as an augmented matrix. And another way that's useful to represent it is as a matrix equation. Oops. Oh, geez. Okay. So taking the matrix of coefficients times the vector of unknowns equals the vector of the right-hand side. So we want to define matrix vector multiplication. So that multiplying these out will give us the left-hand side of our linear system of equations. Now, when we were looking at the column picture earlier, remember how we managed to rewrite the left-hand side as a combination of the columns AC and BD. So that's the left-hand side of our system of equations. We're saying that we want the matrix of coefficients times the vector of unknowns to equal this. And then we can generalize that to matrices of other sizes other than size 2x2. So in general, if we have a matrix A whose first column I'm going to denote by A1, let's say the second column is A2, and let's say it has n columns altogether. Okay. And then let's say that I have a vector x with n components, x1, x2, xn. We define AX to be x1 times the first column of matrix A plus x2 times the second column of A, and so forth. Okay. So matrix vector multiplication is defined to give you a linear combination of the columns of A. Okay. Now, in order to multiply a matrix and a vector, it's worth noting that the sizes have to match up in a certain way. Namely, the number of columns in A will have to match the number of components in X, so that you can actually multiply them using this formula or this definition. All right, so let's do just one example. All right, so up until the first exam, you guys are primarily concerned with square matrices, but after the first exam, you're going to be working a lot more with rectangular matrices, up until the second exam, I would say. Okay, so here I've got a size 2 by 4 matrix, 2 rows, 4 columns. Since it has 4 columns, if I want to multiply it with a vector, that vector will have to have 4 components. So it'll be size 4 by 1, 4 rows, 1 column. So to multiply this matrix with this vector, so remember the result is a combination of the columns of the matrix. The scalar multiples of the columns come from the components of X. So I've got x1 times the first column. This is x2 times the second column. So then we'd have plus x3 times the third column. And then finally plus x4 times the fourth column of our matrix. So now we can add this up. So it'll be 2 plus 6 plus 1. So it'll be 9. And then 6 minus 3 minus 4 minus 2. I think that's negative 3. Okay. All right, it's maybe worth noting that the result is size 2 by 1. So if you want to know what the size of the result is going to be, you can get the size of the result by looking at these sort of outer numbers, if you will. So these tell you the size of the result. All right. Now there's another way that you can view matrix vector multiplication. Okay, so here we compute it as a linear combination of the columns of A. But an alternative perspective, if you will, on multiplying a matrix and a vector. I'll just use the same example to illustrate. So we can compute the result of this product one entry at a time. So the way it works is that the entries of the result are the dot products. Between the rows of matrix A with vector X. So to illustrate what I mean by that, if we take this vector, the first row of A, and think of it as a vector 1, 2, 0, 1, and then we dot it with the vector 2, 3, minus 1, 1. So remember dot product, it's 1 times 2 plus 2 times 3 plus 0 plus 1. So that gives you 2 plus 6 plus 0 plus 1. And you see it's the same as what we did up here. 2 times 1, 3 times 2, 0 and 1 to get 9. And then if you do the dot product of the second row and x, so 3 times 2 plus negative 1 times 3 plus 4 times negative 1, and then plus negative 2 times 1. Okay. And so you see it does get you the same result as we got from earlier as well. So these are two ways that you can multiply a matrix and a vector as a linear combination of the columns of A, or as dot products between the rows of A and the vector X. In practice, I think it is easiest to use the dot product of the rows of A and X method in order to multiply. But nevertheless, it's important that you still know that matrix vector multiplication forms a linear combination of the columns. So keep that in mind because it does come up again and again throughout this course. Now, finally, I want to talk about one more topic, which is linear transformations. So first, I want to introduce a little bit. Actually, I'll say one thing about matrix vector multiplication before I get to linear transformations. I should note some properties. Okay, so matrix vector multiplication is distributive. So if you have A times vectors U and V, That's the same as A times U plus B is the same as AU plus AB. Likewise, if you have A times a scalar multiple of a vector, you can multiply A with B and then multiply the result by scalar C. So you can sort of pull the scalar outside. Okay. So those are just two properties of matrix vector multiplication. And now I'm going to talk about linear transformations. All right, so first I want to introduce a little bit of notation. All right, so if we have a notation like this, so what this notation is saying is that we have a function f. Its inputs are vectors in Rn. So that's what the first Rn is telling us. And then this Rm over here is telling us the outputs. So the outputs would be vectors in Rn. Okay. So in other words, the input will have n components and the output will have m components instead. So this, I've seen some people call this the signature of a function. So then as an example, if I have a function, say f of xy equals x squared plus y squared, sine of x, cosine of y, e to the x plus y. Okay. So the signature of this function here so the number of components in the input is 2. So you can think of the input as a vector in R2. The output has 3 components. So it's a vector in R3. So then this would be the signature of this function f up here. Okay? All right. Now let's suppose that we have an m by n matrix, m by n matrix. Then we can define a function t of x equals a times x. Now since a is size m by n, the vector x will have to be size n by 1, because remember the number of components of x has to match the number of columns in A. And then remember that the size of the result is given by the numbers on the outside. So the result is size m by 1. All right, so that means the signature of this function t so it inputs a vector from Rn, and then it outputs a vector in Rm. Okay. So every m by n matrix gives us this function with signature from Rn to Rm. So I like to remember this just by remembering that's flipped. If A is size m by n, t is Rn to Rm. Okay? All right, let's just look at an example. Let's say I have a 2 by 3 matrix. All right, so with this matrix, I should be able to define a function with signature R3 to R2. So this function is going to take a vector in R3, and it's going to output matrix A times the input vector. Now let's actually do the matrix vector multiplication. So I'm going to do dot products with the rows of A and the vector X. So dot product will be X plus 3Y, and that will be the first component of the product. And then next we get 2X minus 2Y plus Z. All right. So then this would be a more explicit formula for our function. Of course, some people might write it as a comma separated instead. So remember I talked about how these are the same thing. At this point, it's probably going to be more useful to think of vectors as columns in this class. So it'll be good to kind of get used to this. All right. Now, when we look at this function here that we defined, I want to note two things about this function. It satisfies t of u plus b equals t of u plus t of v. Then it also satisfies t of cu, so c is a scalar multiplying vector u. It's equal to c times t of u. So you can pull the scalar outside. So of course, these are basically a restatement of the properties of matrix vector multiplication that I mentioned just a little while ago. This is just reflecting that matrix vector multiplication is distributive. And here, again, this is just saying you can pull the scalar out to the front. Any function t that satisfies these properties. Well, I guess I don't need t. So any function satisfying these properties is called a linear transformation. You'll also see linear mapping for the same thing. And what we've seen right now is if our transformation has this form, so if our transformation simply multiplies the input vector by a matrix, then this function is linear. Now, the reverse happens to be true as well. So if T is a linear transformation or a linear mapping, or just linear map as well. Let's see, I'll be more precise. So if T has signature Rn to Rm, okay, then there must be some matrix A such that T of x is equal to A times x, okay? So we're not necessarily going to do too much with this result in this class. This review is already running a little bit long, so I'm also not going to prove it. But I do want to say that this result is very important in mathematics, which is why I'm highlighting it at least. Yeah. So if your function multiplies the input vector by a matrix, then it is linear. But vice versa, if your function is linear, meaning it satisfies these two properties, then it must have this form where it multiplies the input by a matrix, okay? All right, so looking back at this example, so we have this function and we started with, this matrix and we multiply it with this vector to get this result. If you want to work backwards now, and we want to find the matrix of this transformation, i.e. we're looking for the matrix A, such that T of x is AX. Okay. So it's pretty easy. If you have the output of your transformation, if you just read off the coefficients of x, y, and z, and you take those coefficients and just put them into a matrix as columns. So say the coefficients of x were 1 and 2. Likewise, if you look at the coefficients of y, they were 3 and -2. And then you look at the coefficients of z, which are going to be 0 in the first component, and then 1 in the second component. Then this gives you the original matrix A that we started with. Okay. So then this matrix here that our transformation multiplies the input by, this matrix is called the matrix of the transformation T. And so you might see this notation for that sometimes. So this notation is saying like it's the matrix of the linear transformation T. All right. So I'll just do one more example. All right, this time I'll start by writing out the end result. Okay. All right, so if we want to find, so this function here is a linear transformation. You can always tell if it's a linear transformation when you look at the outputs. None of the variables should be raised to any power, and they should just be added and subtracted. And like maybe multiplied by scalars as well. So basically each component should be additions or subtractions of scalar multiples of the variables. Okay? So if that's the case, then T is linear. It's not super important, but the signature would be R4 to R3 in this case, because there's 4 inputs and 3 components to the output. So the matrix of T, first, I can already say the size is going to be 3 by 4, because remember it was opposite from what you had in the signature. And to get the matrix of the transformation T, you just look at the coefficients of x1, then x2, x3, and then x4. So the coefficients of x1 are 3, 0, and 2. The coefficients of x2 are -2, 1, 0. Coefficients of x3, 1, 1, -2. Coefficients of x4 are 0, -1, and 1. Okay. So then this would be the matrix of the transformation T. If you take this matrix and you multiply it with x1, x2, x3, x4, then the matrix vector product will equal the output of your transformation, okay? Now, it's really easy to get the matrix of the transformation just by reading off the coefficients. I do want to point out another way that you can find the matrix of the transformation. Okay, so if you apply the transformation to the vectors 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. Okay. Okay, so you can see how these work. You have 1 in one entry and zeros everywhere else. Okay, so if you plug in 1 for x1 and then 0 for x2, x3, and x4, you should get 3, 0, and 2. Okay. If we plug in 1 for x2 and 0 for everything else, all right, so 1 for x2, 0 for everything else, you'll get -2, 1, 0. Likewise, plug in 1 for x3, 0 for everything else. You should get 1, 1, -2. And finally, plug in 1 for x4 and 0 for everything else. You should get 0, -1, 1. And if you compare what we have here and what we found over here, you see that these are the columns of the matrix of the transformation T. So you can get the matrix just by applying it to these vectors. in general, if we let E1 denote the vector that has 1 in the first component and then zeros everywhere else, E2 is the vector that has 1 in the second component and zeros everywhere else, and so forth. And then let's say we're dealing with vectors in Rn. So the final vector En would have zeros everywhere except the very last component. So these are called the standard basis vectors of Rn. And then if we have a linear transformation from Rn to Rm, then to get the matrix of the transformation, the first column of the matrix will be the transformation applied to vector E1. The second column will be the transformation applied to vector E2, and so forth. All right.